Section 4.6 is kind of a good one to cover right before an exam because a lot of it's going to be a review of stuff that we've already done. The new part is just to really learn how to use technology to complement the things that we've got so far. So let's take a look at what it's all about. We're going to start with working with the graph of 4 sine of x plus cotangent of x. So let's plug that into our graphing calculators. Now, of course, you can't plug in cotangent directly, so I'll plug in 4 sine of x. Make sure that your calculator is in radian mode. The TI-84 will show you right at the top that, okay, yeah, you're in radian mode. So 4 sine of x plus cotangent of x. What am I going to do to graph cotangent of x?
1 over tangent.
Yeah, 1 over tangent. You could also do cosine over sine. That would work. So, but 1 over tangent is pretty good. I like that. So we'll go with that. 1 over tangent of x. Great. But we're also going to want to deal with the first and second derivatives too. So let's get our calculator to graph the first and second derivatives. So go down to the second line here and hit the math key, and then the 8th option is numerical derivative. So press the number 8. And it should give you something like this. Now, if you've got an older 83, the display is going to look a little bit different. If your 84 isn't up to date with its operating system, again, the display might look a little different. So you're differentiating with respect to x, and we want to type in the function. You've got 2 choices here. You can either type in the whole function as is, or we can be clever. What do you want to do? I'm be clever? All right, let's be clever then. We want to differentiate the first derivative, the first function, y1. We can tell the calculator to do that by going to the vars key. So hit the vars key, and then cursor to the right once to get to y vars, and here press enter twice. First one gets you to this menu. Second one chooses y1. You can type the number 1 twice. Let's see. There we go. So y1, great. Last but not least, I want to differentiate this at x equals x. This is not the way they intend this thing to be worked, I'm sure, but basically what this will do is it'll graph your derivative, which is really cool. We don't even have to calculate it, it'll just graph it. How about that? Now, as far as graphing is concerned, let's shut this graph off at least initially. I'd like to look at what the function looks like before I look at the graph of the derivative. So I can do that by pressing the enter key right here. If you cursor away from that, you'll see that, okay, yeah, we're not going to graph this one. It's not highlighted like the first one is. As far as graphing the first one is concerned, we'll have to set up our window. But since we're here, let's repeat this and look at the graph of the second derivative. So how are we going to do the second derivative? Well, second derivative is the derivative of the first derivative. So let's go back to the math key, down to option 8, derivative with respect to x. But I don't want to put y1 here anymore. What do I want to put? y2. So let's go back to that menu. Vars, cursor to the right once, y vars, press 1, and this time press 2. That'll differentiate the second derivative, or the first derivative, with respect to x again, and bam. Now I am going to shut that graph off, so I'm going to go over here and press enter on the equal sign. Initially, I only want to look at just the first derivative, or I mean just the graph, not any of the derivatives. As far as the derivatives are concerned and the graph is concerned, let's look at it in this window. Negative pi to pi. I mean, they gave you the window that you want to look at, so let's use it. So I'll go up to the window key. Let me clear this stuff out here. All these keystrokes. If you need to follow along, you can. Let me just clear that out so it doesn't look so busy. Window, negative pi. Make sure you use the opposite key on the bottom of the calculator. Negative pi to pi. After you press the enter key, it's just going to replace that symbol with decimal value. Sometimes it's convenient to put like the scale on the x-axis to be something, you know, useful or helpful. Say like pi over 6 or pi over 4. So I'll just simply do pi over 2. So about 1.57. As far as the y scale is concerned, you know, it's a little bit of a crapshoot. What's the trick that I've suggested to you guys before with the y-axis? Zoom 0. Now, it may or may not work too good, but you know, it's a place you can start. You can try and figure out things from there, and it's not looking too good. It's like, all right. If you look back at the window, you can see y min and y max have been adjusted to be some number in the hundreds of millions, maybe even billions. So let's calm that down a little bit, maybe go from -6 to 6. That's just a guess. We might have to play with that and adjust it some more. Okay, that looks a lot better. All right, so that's kind of a nice rough shape of the graph. One thing that you might notice about this graph is something about its domain. Take a look at this graph. It seems like it's probably going up and up and up and up right here at 0, and then down, 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 and down at 0. What kind of feature does it look like the y-axis is for this graph? Looking like a vertical asymptote to me. And if you think about the cotangent function, cotangent is not defined at 0, so wouldn't be surprised to see a vertical asymptote there, and in fact that's what's going on. So great, there's our graph. That's our function. Let's see what we can learn about this graph by looking at the first and second derivatives. So I think on this on the handout, looks like I've got the graph of the function. So that's just your function. But the first and second derivatives can tell us some interesting things about this graph. So let's see what we can figure out. Let me pause for a second. Are you guys up to speed with, you've got the graph, the first and second derivatives programmed in? We're good on that part. All right. Let's shut off the graph of the function and now take a look at the graph of the derivative. So come back to your equation y1, press enter, shut that graph off, go down to y2, press enter, turn that graph on. And now when we hit the graph key, you see the graph of the derivative. Okay, so wow, kind of wild there, a lot of stuff going on. What does it tell us? What does this first derivative tell us about this function? Where it's increasing and decreasing. Yeah. So as far as where it's increasing or decreasing is concerned, how do I know if a function is increasing or not? All right, so it's got a positive first derivative. So there's a little spot right here and a little spot right here where the first derivative is positive. Great. But where is that? You can do the trace key and kind of get close to those values, like here, all right, but you're not really exactly there. And what I'd like to do is I'd like to find those exact values. So let's do that. So if you want to find those exact values, then we're going to go to the calculate menu. So second, and then calculate. I want to know where the root is. Root also goes by the name of 0. The x-intercept, root and 0, those are all synonymous. So select the second one from the calc menu. Again, you get the second key and the trace key that takes you to this menu. Then I'll select option 2. Your graphing calculator is going to ask you to come up with a little window. It's like, all right, well, where should I look for your root? Between what values and what value? So you're going to go a little bit to the left of the root. And I know I'm to the left of the root because my y value is negative. When you get a little bit to the left of the root, press enter. Then you got to go a little bit to the right of the root. And you just got to go far enough that you got a positive value, so it's changed signs. You press enter, and now the calculator says, okay, I'm going to look here. And it's going to ask you for an initial guess. Don't work very hard at all. Just press enter again as your initial guess. Let your calculator do the work. It's not that hard. And it should come up with this value for the root, 0.57798. Raise your hand if that's showing up on your calculator. All right, good deal. If it's not, and if you got lost someplace, please reach out and get some help, because this is stuff that I'd like you to be able to do. So let's write that down, 0.5779. That's one of our roots. Let's see, 0.5779. And let's do that again for this other place over here. So maybe I'll, let's do it this way. Second calc, and then 0 again. I need to get a little bit closer to the root, so I'll get a little bit closer. That's close enough. Doesn't have to be terribly close, just as long as the root is someplace in between your left and right bound. Press enter for the left bound. Cursor to the right a little bit, press enter again. You don't have to have the same left and right bounds I do. Once you get that, press enter one last time and we get 1.2978. All right, so those are our intercepts of the derivative. Now you got to take note of what's going on here. Between 0.5779 and 1.2978, the derivative is positive. What's that telling me about the function then in that interval? It's increasing in that interval. Perfect. So let's kind of keep track of that with a little diagram like we've done before. All right, so x, f, f prime. Actually, you know what? It's probably going to be a long one. Maybe I'll just do all of it right here. Now, I'm not going to repeat these calculations. These points here on the left side of the y-axis are going to be mirror images of those points on the right side of the y-axis. So let's fill those in as, let's see, negative 1.2978, and then negative 5779, and then positive 0.5779, and then 1.2978. This is where the derivative is 0 at all these points. There is kind of good news. We don't really have to test points in between, so we can just look at the graph for that. So the derivative is 0, 0, 0, and 0. Nice. Now to the left of negative 1.2978, what's the sign of the derivative?
Negative.
Negative. And you just get that by looking at the graph. All right, to the left of this point, it's negative. So it's negative. And then for a brief little bit, it's positive. And then negative again. Yeah, you know what? Technically, I guess I probably should have maybe put 0 here. Even though 0 is not in the domain, it is a place where the derivative can change signs. Fortunately for us, the derivative is negative to the left of 0 and to the right of 0, so it doesn't matter exactly too much. But then positive, and then finally negative again. So wow. But we've got a lot of information now. We know that the function is increasing, then decreasing, excuse me, other way around. Wait a minute. Wait a minute. This should have been negative, right?
Yeah.
There we go. So it's decreasing. And then increasing. A lot of times functions will alternate sign in terms of increasing and decreasing, but not always. Decreasing, increasing, decreasing, decreasing again on both sides of 0. And then increasing, then decreasing. What does that tell me about some of our points here? What do we know in particular about the point here? Local min. And the point over here, local max. And then similar over here, local max. No, wait, local min. And then this one's your local max. Do I need to write down all the intervals where it's increasing and decreasing? You guys handle that? You're good on that? All right, great. Let's turn our attention to the second derivative. So to do the second derivative, what do you think we need to do?
Turn it on.
Yeah, turn it on. Let's shut off the graph of the first derivative. So I'll come over here, shut this one off. I strongly suggest you don't look at more than one graph at a time with these things. It just gets a little bit confusing and messy. So I'll shut off the graph of the first derivative, turn on the graph of the second derivative. I should be able to use the same window. So when you're ready, hit the graph key and bam. All right. These little pieces are interesting. I think this is your graphing calculator's attempt to draw a vertical asymptote. But let's try and find these points here where the graph nicely crosses the x-axis. These other vertical bars, I think those are just your graphing calculator's attempt to draw a vertical asymptote.
Yeah, when I did a web design, it didn't matter. I checked to make sure we only need those 2 points, right?
Yeah. So there's 2 points here that we're going to worry about, and we're going to find those the same way we did just a minute ago. So you're going to hit the calc key, second, and then calc. Want to find the 0, and to type in. You can just type in a number if you happen to know it. No, don't remember the scale here, so I'm just going to kind of cursor to it. So someplace to the left of your root, and then someplace to the right of the root. When you get those, just press the enter key and bam. So you get negative 0.8576. Now once again, 0 is not in the domain, but the function can change signs at 0 because 0 is an asymptote. So I'm going to put 0 down on my little list like I probably should have done with our first derivative. And then finally I need to know this other point. I don't know as I can get that one by symmetry or not, so let's trace over to there, see if we can't find it. So second calc again, want to see the zeros. So just go to the right until you see your cursor come back onto the screen. There we go. That's pretty good for a left bound. I'll press enter. And then to the right of that point, I'll press enter again. And this time 0.857, yeah. Okay, so I do get symmetric points. I wasn't sure about that. So let's write all three of those down. So we're going to make another table for this graph. X, F, F double prime. So the function is 0 here and 0 here. This is, should say the second derivative is 0 and 0 here. Over here, do you remember my symbol for it does not exist?
No, backwards E.
The backwards E with a little slash through it. That point doesn't exist on the second derivative, nor does it exist on the first derivative because the first derivative is not defined, or excuse me, the function is not defined at that point. All right, let's fill in some information here then. So to the left of negative 0.58576, what's happening with the second derivative? Is it positive or negative? There, positive. So coming back over here, it's positive and then negative. What happens to the right of 0? When you go to the right of 0, it's positive. And then to the right of 0.8576, it's negative. So you should get something like that. The second derivative no longer is telling us something about increasing and decreasing. What's it telling us about?
Concavity.
Concavity. Great. So what's going on to the left of 0? Concave up, concave down, concave up, and concave down. Excellent. That does tell us some more information about our graph. What does it tell us? Inflection points. How many inflection points do I have? 2. Nice. Just 2. All right. So we've got an inflection point here. And an inflection point here. How come 0 is not an inflection point? Because it goes from, you know, concave down to concave up.
Just literally an asymptote.
Yeah, the graph isn't defined there. So it can't be an inflection point if it's not defined. So nice, nice. Let's look back at our graph on an exam. I'd want you to label some of the important points. So, you know, for instance, that one would be a local min. Here's your local max. Local min, local max. I'll give you much more room to do it than you've got here. But then we should also probably take care to get the inflection points. And again, you'd have more room on that to do that kind of thing. But it's nice to be able to use technology to try and find these things. And it gets easier with Desmos. Drew?
For inflection points, do you want us to give it like an XY coordinate or?
So let's see, our inflection point was at negative 0.856. So it's probably going to be around here someplace. There's your inflection point.
But do you want us to like plug in the X value back into the
Yeah, I guess it depends on the question, the way I ask it. If I ask for it, then yeah, you should be able to get it. Now, if you needed to find the Y coordinate at a point like your local min or local max, let's look back at your calculator. So, let's see. Suppose I wanted to find, well, gee, what's the y coordinate, you know, at a particular point. Let's do this one, 0.8576. Well, you could do this, you could go to the table function, and hopefully you have your calculator set up the way I do. Let me just review those settings. At table set should be set to independent, is ask, dependent is auto. When you go to the table, you can just type in whatever number you want, 0.8576. Now, this isn't the value that I want. Can anyone tell me why it's not the one I want? That's y3. That's essentially 0, which is giving you a number in scientific notation, 9.5 times 10 to the negative 6. That means there's 5 leading zeros. But the biggest problem with that is that it's y3. We've got to go back and turn on our graph for y1. I mean, you can take a look at y2 and y3 if you want, but really what we're interested in is in this first column, which is your y1. That's the actual value. If you want more digits, cursor over there. And that'll show you as many digits as I could possibly want. So, good question. Good question. Yeah, please.
You're saying that if you did ask for a y value, we could just find it on a table, we wouldn't have to like plug it in and then show that?
Yeah, now with one of our y values, I think it was 0.5779, I think that's square root of 3 over 3. But let me just kind of check here. Square root of 3 divided by 3. Oops. Divided by 3. All right, it was close. I'm surprised it's not a more familiar number. In any case, yeah, you can plug them into your calculator.
Thank you.
Yeah. Any other questions on that first one? Let's keep going with example B. Do you want to practice it on the graphing calculator or do you want to try it on Desmos? Calculator? All right, we'll do one more on the graphing calculator and then we'll switch over to Desmos. But I do want you to know how to use your graphing calculator very well because when you go to Calc 2, you might not find somebody as Desmos friendly as I am. So let's move on to this function. Square root of x over x squared plus 3x plus 8. All right. All right, so let's clear out this function. Probably a good idea for this one would be to hit the alpha key and then the y equals key. And then choose the first option there. That'll allow you to draw a fraction without having to worry about all the parentheses and stuff like that. So alpha and then y equals, that gets you this menu. Just press enter or type a 1. You've got a nice fraction, nice horizontal fraction from which you can type in the square root of x over x squared plus, or is it 3x plus 8, I think it was? Yeah, plus 3x plus 8. And the cool thing is that we've already got our first and second derivatives set up. So that's the nice thing about doing that y1 and y2 bit, is that when you update your function in y1, you don't have to mess around with y2 and y3. Okay. Probably should keep in mind one thing about the domain. There's two things you would worry about in this function. The first of them is the denominator equaling 0. I don't think that's going to happen. I don't think this graph's going to cross the x-axis. At least the graph of y equals x squared plus 3x plus 8. In fact, let's just kind of test that real quick with Desmos. Y equals x squared plus 3x plus 8. All right, so it doesn't cross the x-axis.
You put the square root.
Oh, I didn't want the square root. I'm just testing the denominator. Notice that this graph doesn't cross the x-axis. For instance, if I had a graph like y equals x squared minus 2x minus 8, that graph crosses the x-axis at two places, at -2 and 4. So that would mean those would be points in my domain that I couldn't use. Those points wouldn't be in the domain. So that's one of my concerns in terms of graphing this function. What's the other concern that I might have in terms of the domain? Perfect. Anything less than 0. You've got a square root in the numerator. So as far as my graph is concerned, I'm going to reset my window to be, I don't know, let's go 0 to 9 maybe. You know, that would be fine. That's a good start because I know that the graph is only going to exist for positive values of x and the number 0. Let's try that window trick again. That is zoom 0. I'm thinking it might work a little bit better for this one than it did the last one. So if I hit zoom and then 0, let's see, what's wrong here? Go to. Really? It's not liking this one, is it? This is a surprise here for me. Anyone else getting that same error that it just?
Yeah. Oh no, it just popped up for me.
What's that?
You have to check the window.
Window 0.
Because you scale.
Could it be because
No.
all three are on?
What's that?
Could it be because all three of your things are on?
It took a minute for my.
It should-
Trying to zoom, are you zooming to 0 when it's not?
Oh, yeah. Here, let's just do that. So, you know, it should do all three, but let me try this one more time. Graph. All right. Zoom 0. See if that works. Okay, that works. So we got this nice little graph here. Wonderful. But now we want to know some things about it, like where is it increasing, where is it decreasing, where is it concave up, where is it concave down. There's a lot of information we can figure out about this graph. But I mean, you look at it. If you had to put your finger on the spot where it changes from concave down to concave up, could you do that? You might be able to come close, but it's hard to actually know exactly where to put it. There's one thing that can tell you where to put that. What would it be? Second derivative, right? Where the second derivative goes from negative to positive, that's where your inflection point is going to be. That's where it's going to go from concave down to concave up. So we'll figure those out one at a time. Let's start by graphing. We're looking at the first derivative. So I'll go back here and I'll shut this off. I'll turn this one on. And I'm going to do zoom 0 again because I don't really, it's not liking that one. It's just not liking zoom 0 with this at all. So I think the thing to do then is to try and just guess at what the window might be. Might have to readjust this. Let's go from -3 to 3. I don't know if that's a good guess. It's still not liking it. Boy, that's weird.
Maybe has the derivative from the first function we did.
No, because it should be differentiating the function I have up above. Yeah, I'm kind of stuck on that one. Let's see, let me one more thought here. There, window. You know, I'm not gonna hit zoom 0. I don't know, we already tried that. Let's just try it one more time. Window. Let's try it again, 0. You know, I think it doesn't like x equaling 0. I think that's the problem. So if I set my window up to like 0.1, then the graph actually worked. I'm gonna zoom in to like negative 0.5 to 0.5 on the y-axis. See if I get a good graph there. Wow. So what's going on with this graph is that it's really, really close to 0. And to get this to graph, I made my x minimum 0.1. Because for some reason, and I think you can understand what's going on, for some reason it's just not able to calculate the derivative near 0. So with that window as a 0.1, we get this graph. It's still not very easy to see this thing, is it? What we need to do is we need to zoom in a little bit on the y-axis. So I'm going to change my window again in the y direction, go from negative 0.2 to positive 0.2. And let's see what that does for our graph. Well, you can see a little bit now, a little bit better. If I were to make one last change, I'd probably go down to negative 0.05. I just don't think you need to go very far down to see this graph. And we're starting to see a little daylight between our function and the x-axis. So if you want to see my window settings again, here they are. Let me get rid of x scale of pi over 2. We're no longer working with the trigonometric function, so I'll make x scale equal to 1. So my window is going from 0.1 to 9 on the x-axis and negative 0.05 to 0.2 on the y-axis. Let's take a look at that graph. This is the graph of the first derivative. What information do I need from the first derivative to help me out here? Yeah, I need to know where it crosses the x-axis again. So that's going to be this point. You can find that from the calculate menu. Second, calculate. 0. And I need to cursor over here to a left bound. So someplace to the left of this, it's going to be positive. Move to the right until you see the y value is negative. It's negative, that's fine. Move to the right of it, it's changed signs. And finally for the guess, just press enter one more time and we get 1.2078. So that's a critical point at 1.27 or 2078. To the left of that, the derivative is positive. To the right of that, the derivative is negative. I don't think the derivative comes back. I think it's, yeah, let's see, does it? Window. I don't think it's going to come back above the x-axis.
I went similar to that other time, it didn't go back, it was just that one point.
Yeah, okay. All right. So Dean's telling us that he checked it out and it didn't ever come back and touch the x-axis again. So if I graph this a little bit farther, yeah, it's still staying underneath. It's tough to see, but it is still staying underneath. So it only changes signs at that one point. To the left of it, it's positive. To the right of it, it's negative. So that tells us where the function's increasing and decreasing. So it's increasing between 0 and 1.2078. I think WebAssign would include a square bracket at 0. And then 1.2078 parenthesis. And it's decreasing at 1.2078 to infinity, so it's decreasing the rest of the way. Bracket or parenthesis at the 1.2078.
Right.
Parenthesis. Manuel, question?
Why is there a bracket at 0?
I'm pretty sure that's what WebAssign's gonna want. It's not necessarily what I want, but
Cause
it's,
isn't the domain, cause like,
the domain starts at 0.
oh wait, my bad, no, I'm tripping, cause
Yeah.
I forgot the 8 there, my bad.
So the domain starts at 0, and I think if you look at the point of view from just the right, it is increasing at 0. But at this critical point, we're gonna use a parenthesis. It's neither increasing nor decreasing there because that's where the derivative is 0.
Yeah.
Now let's work on the second derivative. We're okay with the first derivative. All right, so let's take a look at the second derivative. I'll shut this one off. Turn the second one on. Let's see. I'm not sure exactly what to think about the y values here. I'm just going to open it up to -1 to 1 on the y-axis, and maybe 0.25 for y scale. All right, so similar behavior with the second derivative that we saw with the first derivative, that it's pretty flat after a while, after a very short while. So I'm going to need to zoom in a lot on this y-axis. Let me show you a different way to zoom in that might be a little bit more user-friendly or easy for you. So instead of changing the window this way, I'm going to click the zoom key, and then the first entry here is zoom box. So zoom box, and I'm just going to go to the right a little bit, and then just a little bit down, a little bit south of the y-axis. Your cursor doesn't have to be in the same point as mine. Just move it someplace off the line below the x-axis and press enter once. After you press enter once, you can cursor up and to the left, and I'm going to drag out a very skinny box. That skinny box is going to be my new viewing window. So it's a nice way to zoom in without having to guesstimate, what x and y values you're going to need. So when you press enter again, that's your new window, and bam. So kind of like the first derivative, it looks like it's going to cross the x-axis at one place. All right, so somewhere here to here, I cross the x-axis again. So you can see that the y value is positive here and negative here. So somewhere in there I crossed over a root, and it's flat and positive the rest of the way. Let's find that root. If you wanted to, you could play the zoom box trick again and zoom in a little bit more just to kind of get a better idea of where that's happening. So just choose a very narrow box around that. So I'm not going very far above the x-axis. And should be good enough. There we go. Now you can see it. Now you can really see it. Let's find that root. Second calc, 0. Left bound, then right bound. How's things going on, my TI Inspire fans? Okay?
Yeah, pretty good.
Okay. So about 2.6179. So so to the left of 2.6179, the second derivative is negative. So from, say, 0 to 2.6179,
Concave down.
yeah, it's concave down. And then concave up from 2.6179 to infinity. So you got your concave down and your concave up. What's that tell me about 2.6179?
Inflection point.
Yeah, it's your inflection point. And what other kind of point did we have for this graph? Yeah, we had a, let's see, we went from positive to negative, so we had a local maximum. Actually, I think it was probably a global maximum, if we were to look at the actual function. So here, we go back there, type that in. Zoom 0. There we go. So yeah, you do have a global maximum at that point. Now the book calls it an absolute maximum. So local slash absolute maximum at x equal 1.2078. Nice. So you're getting all the information out of this graph. You're just not getting your hands dirty calculating first and second derivatives and then trying to solve this kind of stuff. We're using technology to do that part. Yay.
So like in the test, would you like want us to like either way works in the test?
You know, there's going to be problems that I want to see some actual calculations for and stuff like that, but there's definitely going to be one where I just say use technology.
Okay.
Now that technology could take the form of a graphing calculator. Like I said, I think that most of you are going to be stuck using a graphing calculator for your Calc 2 class, so that's why I want to spend some time on it. But let's also take a look at the convenience of Desmos, because Desmos makes this a lot easier. All right, any other questions on example B? All right. Let's take a look at example C. And like I said, we're going to do this one on Desmos. Now, if you're going to do this on Desmos, then when you're graphing something like x squared minus 49 times e to the arctan x, then you want to type it in with a function name like f or x, or I mean f or j, or you know whatever works for you, whatever letter. So we'll just use f of x equals x squared minus 49, and then it's going to be times, which is understood there, e raised to the arctan of x. So wow, kind of a wild looking function there. Now if you're wondering how I'm able to adjust just one axis on Desmos, you hold down the shift key and then you use your scroll up and down with your cursor on the x-axis or the y-axis to adjust the y direction. Move to the right, you can do likewise to adjust the x-axis. So it's pretty nice. You can come up here to the toolbar and click the solid A or the capital A to get a darker, more pronounced graph. I think that's helpful. But overall, I think we've got a good idea of what the shape of this thing looks like. So, you know, it's kind of nice. All right, as far as the graph is concerned, we've got the graph. But the real information that we can get from this is going to come from the first and second derivatives. So I need to graph the first derivative. Now remember what we did for graphing this on the graphing calculator. Here it is on decimals. Y equals f prime of x. Ooh, ah. That was pretty easy. I like that. And in fact, there's a couple other things that are really nice and easy about using decimals here. For instance, if I want to know where the root is, I just tap on the graph. I tap on the graph here. And I think that's it as far as where this graph crosses the x-axis. It's just this place and this one.
That's not, is that a zero? The one on the left?
Actually it's no, it's not a zero. It's probably a maximum at some point. Let me try and zoom in a little bit. So yeah, it only crosses the x-axis one place, and that's all we got to worry about. I mean, this might be of an interesting point if we were looking at the function, but it's the derivative. So the only point that really concerns us right now is this one right here, 2.639. So all right, 2.639. That's a critical point. If you're asked to find a critical point, that's just where the graph is zero. So, or the graph of the derivative is zero. So critical point. .639. Okay. Great. And we see that right here. To the left of this, derivative has what sign? Negative. So to the left of this, the function is decreasing. So decreasing Raina, where is it decreasing? What interval should I write? What to what? So we've got 2.639. To the left of that, the derivative is negative. To the right of it, the derivative is positive.
0 to 2.639. Negative.
Negative infinity to 2.639. Good job. Great. And then once we get to this point, for a moment, the function has a little pause, and then it starts increasing. 2.639 to infinity. Cool. So 2.639, that's where all the magic happens. That's going to be your point right here. Let's keep going. Suppose you want the second derivative here. Let's go back and do the second derivative. For the second derivative, it's no harder than the first. Y equals f double prime of x. This time there's two places where the graph touches the x-axis. I don't think it touches the x-axis again. If we were to zoom in on the x-axis, yeah, you can kind of see that. So there's two places. Negative 3.974 and 0.448. Both of those are on your handout. So to the left of that point, the second derivative is positive, and then negative, then positive. So let's write that down for our convenience. Plus, minus, and plus. And see if you can't tell us, or tell yourself, what's that saying about the graph. Alright, so where's the concave up? What intervals? Feel?
Ouch.
It's concave up from negative infinity to
Good.
2.639.
Let's see, what was that point there? Negative 3.974?
Oh yeah, that. And then, you wanna know what's concave down or which?
Just concave up.
And then, from 0.448 positive phase.
Yeah, so this last one to the right of 0.448, so you're exactly right. 0.448 to infinity, so cool, that's our interval for concave up. Then we need concave down, concave down. Mia, where's the concave down?
Would it be, would it be from 0 to?
It's gonna be where the second derivative is negative. So that's right in here.
Infinity.
No, not negative infinity. It crosses over the x-axis at negative 3.974.
So it'd be from negative 3.974 to, it's going down to 0.
Well, you're just worried about where the graph is below the x-axis, and that's happening right here in this interval. That's where it's below the x-axis, so that's where the function is concave down. Where the function is above the x-axis, that is positive, that's where the function is concave up. So that was the intervals that we got just a minute ago. That's where the graph is above the x-axis. Where it's below it, you don't worry about, that it gets down to here or something like that, or it gets up to here. You just worry about if it's positive or negative. That's the only information we're gonna get from this graph that we wanna use right now. All right, so 0.448, I think that was, yeah, 48. So what are the inflection points here?
Would they be like negative 3.974?
All right, so negative 3.974, that's one inflection point. Perfect, 0.448. So if you look back at the graph, we can actually graph those. In fact, let's graph it this way. Coming back here on the graph. So I'll shut off this graph. Let's go back to the original graph. If I wanted to find or see where those inflection points were, I could just plot points. So for instance, I could do negative 3.974. I meant to put a parenthesis in there. So you can graph a point. You can graph points like 1, 3. It'll put a point there. But the point that I want to graph is negative 3.974. And then the y value for that point. How do I get the y value for that point?
Put it in for the original equation.
Yeah, put it in the original equation. So it'll just be f of negative 3.974. And beautiful. That's your inflection point. You can graph the other one the same way. So 0.448 and then f of 0.448. Like I said, it's tough to find these points without necessarily looking at without the calculus. I mean, it's impossible. I mean, you can kind of go, yeah, about here someplace, but this is really showing you where it changes concavity, especially that left one. It doesn't really look very concave up to the left of that point. It just doesn't, but that's what the calculus is telling us. Okay, how are you feeling on these? Your tech up to spec?
I feel a little flustered about the concave up and concave down.
So it's just where it's positive and where it's negative. And that's all we're getting from this graph is where that function's positive, where that function's negative in terms of the second derivative. So let's go back to the graph of the second derivative. It's where it changes signs that we're concerned about. Right here and again here. Those are the 2 points. To the left of that, if you put a cursor on here and drag it, take a look at the y coordinates. What do you notice about them? They're all positive. So it's positive to the left of that point, negative between these 2 points. So where it's negative, the function is concave down. So that's the only information we're going to get. And then to the right of it, again, positive. Drew?
Are we using Desmos or graph calculator on these exams?
I'm toying with the idea of letting you use both Desmos test mode. Now you have to have Desmos test mode. If it's not Desmos test mode, then it doesn't work. So when you download Desmos test mode, let me see if I can't find it on my phone. So you'll see a couple different icons, but one of them should be Desmos if you have that, but Desmos test mode. When you open up Desmos test mode, you have to put it in airplane mode. That way, you know, it kind of blocks some of the information you can get. But once you start it, it says, all right, confirm you want to self-lock this. And what it'll do is it'll start running a timer. And it'll run that timer until you leave the app. Now, if you're going to use Desmos test mode, what I'll do is I'll put a little check mark on the top of your test saying, all right, you're using Desmos test mode. When you're done with the test, you will come up and you will let me, or you will do it yourself in front of me, press the done button, and it'll tell me how much time you've spent on Desmos. And that should match the time that we have on the test. So if we start the test at 9:15 and you hand in the test at 10 o'clock, it should show me that you've been on the app for 45 minutes. If it doesn't, then we have problems. So you might want to practice it before Wednesday to make sure you're okay with that. Yes, sir.
I'm just curious, like, if, like, my phone or, like, iPad or whatever turned off while I was using this, like, just because I have.
Well, you know, I think you can maybe, the screen might shut off, but I think it should stay on the app, really. I don't know if it'll shut off, but let me run this run for another minute. Drew?
It says it's not verified for Mac.
It's something you're gonna do on your phone, not on your Mac.
Okay.
Yes?
So I inputted the one we just did into the Desmos app and then onto the Desmos online, and it gave me two different answers. Like this graph looks nothing like the one it should have online that we just did.
I'd have to look at that.
Pretty sure it's the same thing.
So let's press the done button. See, it says I've been on it for 1 minute. This is what I need to see when you hand in the test. So if you're afraid you're gonna fumble and screw it up, then don't use Desmos test mode, because you know, there's just a lot of technology available to yourself if you're using your phone without running the app. The only way I can be sure that you haven't veered off and Googled something or something like that is by making sure you're running the app. So you need to do that in front of me when you finish. Any other questions or thoughts? All right, let's take a break.